All right, so we're ready to start up again. This next session is, of course, all about you've got your code running. How do you optimize your code? And it's my pleasure to welcome Phil Blood from the Pittsburgh Supercomputing Center to introduce you to the tools and resources available to help you do that. And Phil, thanks for being here, and take it away.
Great. Thank you, Scott. All right, so what we'll be doing over the next little while, as Scott said, I'm from the Pittsburgh Supercomputing Center. I've spent some time over the past few years getting familiar with some tools that are available to help you to assess the performance of your code and to find bottlenecks and then hopefully to eliminate those things that are inhibiting you from scaling efficiently to large numbers of processors. So today we're going to talk mostly focus on those tools and how to detect those performance problems in parallel applications. So we're sort of going to go through a process of performance engineering, and along the way we're going to highlight some of the tools that are available. By no means is this a comprehensive survey of all the tools that are available. In fact, I'll sort of be focusing on tools that are part of a project that I've been part of with the PSC, part of an NSF grant to improve the inner workings between different tool groups, and also to get these tools into the hands of the people who really need them, which is the application developers and scientists who are developing their own code. And it's called the POINT project, and there's some information here. These are the sites and projects that are part of that effort. This is just one group, and I'll also be talking about another tool which has its own grant along a similar lines called IPM briefly. So we'll be sort of hitting all of these things, and the way we're going to do it is we're going to go through this process of the basic process of how you look at profiling your code and assessing performance. And as we go through this process, then we'll sort of hit these tools as we go along, kind of where they're strongest. And they all have different strengths and weaknesses, and we'll try to highlight a few of those. But we will be spending most of the time on sort of the Swiss Army knife of performance tools, which is the Tau performance system at the University of Oregon. This is sort of the background, the basis for what we want to talk about today about this process. And I think it's important in a meeting like this one to talk about the fundamental things. Although we'll be talking about performance tools here, the real fundamental thing is designing a parallel application from the ground up to be scalable. In order to scale to 100,000 cores, you probably won't take your serial algorithm and then just sort of adapt that to run in parallel. You've got to plan from the beginning to have an algorithm that is ISO efficient, that the computation and communication ratio doesn't change as you scale up the number of processors. That as the number of processors increases, your ratio of communication isn't increasing. So these type of considerations are fundamental in the beginning, and those are the most important things. Is the algorithm. So there's this process where you look at that and you assess what sort of an algorithm would enable you would be fundamentally possible to go to 100,000 cores or 200,000 cores. And you look at the science that you need to do and find that best algorithm. That will be the biggest decision. And then you want to try to obviously implement that in an optimal way on whatever architecture that you are looking at running on. Within this process of choosing that algorithm and implementing it, at every point along that process, there's the opportunity to use these performance tools that we'll be talking about. And sometimes that may not be the process that you're in. You may not be designing something from the ground up. You may need to have something you already have, and you just want to make it better than it is. Maybe it's already most of the way there. So there's all different scenarios. So at any point along this path, then you might use these tools to discover how you're doing. And sometimes if you haven't thought too much about the algorithm, or maybe you have, but it just turns out that it was a bad choice, or that it wasn't what you thought it was, tools might reveal the need for a better one. And that's where you can really get some big speed ups, is when you can identify a better algorithm for what you want to do. And so I'm going to show an example of that as we go through this process from real life scenario. So as I mentioned at the beginning, the focus of this of what we'll talk about today is using these tools, becoming familiar with these tools that are available to assess the performance of your code. The solution for is going to be varied. Both for optimizing in serial and in parallel. The solution is going to be very specific to whatever it is you're doing. And so for this type of a general one-day type of event, we're going to focus on the tools that will get you there, so that teach you how to fish. And then there's lots of information available about, once you've isolated where that problem is, what the hot spot, then there's lots of information out there about how to what problems you ought to look for, and these tools will help you to get there. So okay, so with that introduction, we're going to give a little background on the terminology and some of the things we talk about. We talk about performance analysis. One of the things that comes up is hardware counters. So what are these things? Hardware counters are a set of registers on the processor that you're running on. And these registers can count events that happen on the processor. They can count floating point operations, or number of cycles, or cache misses. And different processors have different types of events that they can measure, and they also have different numbers of registers to hold them. And so, for example, a modern Optron has 4 registers for holding different types of hardware counters. So what this means is that you can look at, on an Optron, 4 different types of events at a single time. So you may want to look at cache misses and floating point operations and 2 other things, and that would be it. So you could only measure those 4 at one time. So you'd have to run a bunch of different experiments if you wanted to look at a different set of events on the processor. There's one of the tools I mentioned in the beginning is called PAPI, which stands for Performance API. And this is a standard API for accessing these hardware performance counters. And the idea is that so all these architectures are different, and the hardware counters available on them are all different. And so it's very system specific if you want to get at these things. And so the group at Tennessee has worked on developing a standard API for accessing commonly available hardware counters that are similar across all the different architectures. So this is obviously very useful in facilitating the types of optimizations and tuning that you may want to do, both as an application developer and also if you're designing compilers to do these kind of optimizations. So just briefly to tell you a little bit about PAPI. So the idea is that it's portable, that you can use the same routines, the same API to access common counters across various different architectures. Now, this means that you're hiding some details that may be important. So there's always a trade-off here. These counters are grouped and identified in general classes, but certain counters that are lumped together, maybe in PAPI, might operate slightly differently on different architectures. So you do have to, when you deal with these hardware counters, be careful if to check if you really need to rely on what you're getting, to check to make sure that you really know what that is. And so there's 2 different interfaces available which facilitate this. One is a high-level interface which uses these predefined portable events to access similar counters across various architectures. And this, there's a command when you go on any machine that has PAPI installed, and not all of them do, by the way, because PAPI requires a modification to the Linux kernel in order to work. And so not all machines have that kernel patch installed. So if PAPI is available on that machine, then there's the commands like PAPI avail, which will show you the hardware counters that are available on that machine. That particular architecture, the standard PAPI defined ones that will be portable. If you write a code and to access those counters, they're defined at this level, then it will be portable across all architectures that have PAPI installed. But if you need to know sort of the nitty-gritty of exactly what that counter is doing for a particular architecture, then you can use this command to look at the exact hardware-specific counter events and what they do. So that can get a little tricky, but sometimes you just need to get an overall idea of what's going on. Usually that's the case, is you just need a good approximation of what's going on there to find the problem spots, and so these things work really well. PAPI is also used by a lot of third-party tools, and all of these we'll mention today. For example, Tau, PerfSuite, and IPM can all use PAPI to even hide the complexity of this further and give you access to the information available. So this is just a quick example, just for your reference. If you want to go at the kind of the low-level approach and just count out these events for yourself in your code, and without using any other tools, then you can use, for example, this high-level interface to define the events that you want to look at, so the total instructions, for example, and the total number of cycles, and then you just tell it to, there's a command or a function called PAPI start counters, and then just error checking there, and you do some computation, and then maybe partway through that computation you want to read the values of how many instructions have been issued, how many cycles have gone by, and so you can read them at different points, and then at some point you want to stop measuring. So a simple interface for getting at those counters. And again, you can find these names by issuing this PAPI avail command on the architecture that you want to look at. And make sure you do that on the compute node, because otherwise it might fail or you'll get the wrong counters. So that's just a quick example of how you would do that if you want to get directly at that through PAPI. So, let me just mention too that the format of what I'd like to do today is I'm going to go through examples and sort of this process of the performance engineering and highlight these tools at different points along the way. But then when we come back from the break, what I plan to do is then sort of hit the key points that we talked about and show you, basically just do a demonstration hands-on so you can follow along and do those things. So we'll kind of go through, and I'll tell you about it in this first part, and then the next part you can try to get your feet wet, and we can do some of these things. I can show you exactly the process that I described in the slides. So another thing to be familiar with, we talked about hardware counters, is the different measurement techniques that are available for looking at performance. So